Hey guys, welcome back. Mr. Marone here, taking you through the first notes on trigonometry on our short unit with right triangle trigonometry. And what we're going to look at today are just kind of the introductory stuff and really some solving here that we're going to get some practice with today, and a couple different ways we can solve problems and from missing pieces in right triangles given our trigonometric ratios. So before we do that, one thing we need to highlight are this idea of reference angles. Whenever we deal with trigonometry, we're going to be referencing a specific angle, and we use the Greek letter theta for that reference point. So everything stems off of that reference point. So in this first one on the left-hand side, I'm going to put my reference angle at angle A, and in my second one, I'm going to put my reference angle at angle C. We're never going to use the right angle, angle B, as our reference angle, so we never have to deal with that. Now, when we look at this, when we're trying to label or mark up the triangle based on the reference angle, there's three things that we're going to discuss. One is the opposite side. One is the adjacent side, the side next to the right angle that isn't the hypotenuse. And then we've got our hypotenuse. Okay, and we use just the first three letters of each to abbreviate as we're writing it out. The first thing I always do when I am labeling a triangle is I always reference the opposite side first, the side directly across from the angle of reference. This is my opposite side. The next thing I do is I always go straight across from my right angle, because that's my hypotenuse. And then our adjacent side is our last side. Okay, it is the side next to the angle, but also is not the hypotenuse. We can't have the hypotenuse and the adjacent side being the same thing. And using our abbreviations, with angle C as our reference angle in the second one, straight across from that is my opposite side. Straight across from the hypotenuse, from the right angle is my hypotenuse, and then my third side is my adjacent side. And what we're going to develop when we come back from Christmas break are the reasons behind our three trigonometric ratios. So we have three ratios that we can utilize when we're dealing with these, and we use them to solve various missing pieces. So the first one is the sine, cosine, and tangent. Once again, we use just the first three letters to reference them. So our first one would be sine, and it's always going to be sine of some angle measure. Okay, so there's going to be an angle measure in the triangle. You have to carry that along with the trig ratio, sine, cosine, or tangent. So that's kind of one pair right there. And this is always going to be the ratio of our opposite side over our hypotenuse. Okay? Our cosine ratio, cosine of an angle theta, is going to be our adjacent side over our hypotenuse. And our final one, our tangent ratio, is going to be our opposite side over my adjacent side. And those three ratios together give us what we refer to as SOHCAHTOA. And that's sine is opposite over hypotenuse, cosine adjacent over hypotenuse, tangent opposite adjacent. Just a little mnemonic device to be able to remind us of what each of these values are. So we end up having a couple different ways that we can solve problems like this. So the first thing we can do is simply use our table here is all the different degree measures, and then what the actual ratio for a whole number value from 0 degrees to 90 degrees. Okay? And in here we've got all of our different ratios, so we could use these to figure out what value we're dealing with here. So to give you an example of that, let's take a look at this problem here. So we've got our reference angle, our theta, and they've already marked that we've got our opposite side and our adjacent side. So thinking about this, we're going to have our tangent ratio. We're going to have our tangent ratio. What we can do with that is say that tangent of theta, we don't know what the angle measure is, but we want the angle measure. But that's going to be equal to my opposite side, 2.62 centimeters, over my adjacent side, 2.20 centimeters. And when we simplify that, when I actually divide those, I get the tangent of theta equals 1.19. Okay, and if you reference the table that you were given at the beginning of your notes, you could see that at 50 degrees, we had our sine was equal to 0.7660. Our cosine was 0.6428, and our tangent was 1.1918. Okay, and if you notice, that matches right here. Okay, so that tells me that my actual angle measure, our theta, is approximately 50 degrees using our table. Once I have the actual ratio, I can go to my table and find out what degree measure is associated with that ratio. Now, there is a quicker way to do this. Instead of going to the table every time and having to simplify that, we can use what's called an inverse tangent. Just like when we deal with division and if we've got 2x equals 4 and we need to divide by 2, we're doing the inverse of multiplication. Here we're going to use the inverse trigonometric ratios. So looking at example A, and then I'll let you guys try B and C, we've got straight across is my opposite side. I have my hypotenuse, and that's blank, so we're not going to use it since there's no information there. And I do have information at my adjacent side. Since I have opposite and adjacent, once again, we're going to use tangent. So it's going to be tangent of theta. We don't know what the angle is, but it's going to be equal to 13 over 34. Now, we can't say we're dividing by tangent. What we can say is we can take the inverse tangent. We are going to take the inverse tangent, which is tan, and we use -1 as an exponent to indicate we're doing the inverse. Okay, so we're going to take the inverse tangent here, and we're going to end up with theta on the left-hand side. The tangent and the tangent inverse cancel each other out much like we would. It's not mathematically 100% true that way when we describe it, but that is what eventually happens. We're left with just theta on the left, and we're left with the inverse tangent, tan -1, of 13 over 34. And this just goes straight into your calculator. Your calculator has a tangent -1 button. You have to hit the blue second key and then the tangent key, and then just punch in your normal fraction, and you should end up with theta equaling 20.92 degrees. Okay? Now, one big crucial key here is you must check the mode of your calculator and make sure it is in degrees and not radians. That will give you a totally different answer if it's in radians. To just give you an idea, that same exact problem that we just did in radians is going to give me 0.3652. So it's a totally different answer. So be very careful and make sure your mode is in degrees. So I'm now going to pause the video, and when you come back, you'll see the answers to B and C using this inverse ratio. We can do this with sine and cosine. In this case, the first one we did just tangent. So take a look at those, see if you can find those answers, and I will come back in a moment with the correct answers for you. Okay, welcome back. So as you can see, the second one, they only gave us information at our adjacent and our hypotenuse. So we would use the cosine ratio here and solve out, and we ended up with 38.62 degrees. And our final one over here, we only had our opposite side and our hypotenuse. So we would use the sine ratio. And the same process goes for all three of these. The solving process is identical regardless of which ratio you end up having to use. So this is one of three things that we can search for. We've got, if we look at our different ratios, if we go back to our ratios, we really have three different pieces of information that we can find. Okay, we can find our angle. We can find the angle. We can also find either one of these sides. Okay, we can find either one of them. So when you're doing one of these trigonometric problems, one of those three pieces of information will be missing, and you can solve for it being given the other two pieces. Here's an example of that right here. We've got three of them to do. I'm going to do the first one with you, and then I'm going to let you try B and C on your own. And we'll see how we do. So the first one, if I look straight across from my reference angle, that's my opposite side. Sometimes it helps for me, if I draw a stick figure, thinking of myself as standing at that angle, looking straight across for my opposite side. Straight across from my hypotenuse, there is a blank side, so we're not going to use that. And my third side is adjacent. So I once again have opposite and adjacent. That means I'm going to use tangent. So I've got the tangent, and in this case I actually have the measure 38 degrees equals my opposite side x over my adjacent side 12. Now, if we think back to our table, tangent of 38 degrees is just some value. If you feel more comfortable just plugging in that value, perfectly fine. If you want to stick with tangent 38, that's okay as well. Either way, you're still just getting a value. In order to get x on its own, just like we would solve any other algebraic problem, I'm going to multiply both sides by 12. And I'm left with 12 times the tangent of 38 degrees equals x. Remember that angle has to carry with our tangent or cosine or sine ratio. Now, just so we have it, just so you can see it, the tangent of 38 is going to give me 0.7813. So either way, either one of these is going to give you your correct answer. You plug either one of them into your calculator. Okay, and if you were to just reach for your calculator and plug that in, 12 times the tangent of 38 degrees is going to tell us that x has a side measure of 9.38 centimeters. Okay. So give those next two a try and see how you do. I'll pause the video, and when I come back, you'll have answers for you there as well. Okay, welcome back. So if you notice in letter B, we were given our opposite side of 8 and our hypotenuse of x. So when I set up my trigonometric ratio, I had the sine of 16 degrees equals 8 over x. We would do the same process. We have to get rid of that fraction first, and in order to do that, you have to multiply by our denominator. I multiply both sides by x, and I'm left with x times the sine of 16 degrees equals 8. In order to get x on its own, I have to divide by this sine of 16. Remember, just a value. I've written it here. Sine of 16 is 0.2756. So when I eventually get down to get my answer, I have 8 divided by the sine of 16 degrees, or 8 divided by 0.2756, and I ended up with 29.02 centimeters. And in our last one, it's the same setup as our first one, only we're using cosine. And when you get down to the end, you've got 10.32 centimeters. So let's take a look at a couple of our equivalency ratios when we think about these problems. So if I were to look at, for instance, these first three, they've got a problem. They want us to find some angle measure, sine of x, and it has to be equivalent to the cosine of 63. Okay, so if we look at our table, since we've got this right-hand side one, we're looking for the sine of some value of x. We're looking for x. And the cosine of 63 in our table is 0.4540. Okay? So we need to find 0.4540 in our table, and that ends up being sine of 27 degrees. So x is going to be 27 degrees in this problem. Okay? We can use these ratios interchangeably, sine and cosine specifically, because they work as a pendulum. At 1 degree, sine ratio is really small. Sine is all the way down here, and cosine is all the way up here. So the cosine value for 1 degree is 0.9998, and the sine value is at 0.0175, so really small. But then as we go to 89 degrees, the sine value is going to be 0.9998, and the cosine value is going to be 0.0175. So as you notice, as the numbers go from 1 to 90, the sine gets larger and cosine gets smaller. So all of this allows us to use these sliding scales here that we've got. So let's take a look at 2 and then a 3, and we'll let you try 4, 5, and 6. We'll come back with those answers. So the sine of 34, looking at our table, is 0.5592. And I'm looking for x here. Well, if we look through our table for 0.5592, we end up getting 56 degrees. X would have to be 56 degrees to get cosine there in order to have our answer. So when x is 56 degrees, the cosine of x is the same thing as the sine of 34. And if we look at our table very closely, the sine value of 45 degrees is 0.7071. But that's also what cosine at 45 is. So it's kind of our break-even point. As we slide closer to 90, sine's getting larger, cosine's getting smaller, and they meet at 45 degrees. So I want you guys to try problems 4, 5, and 6 on your own, and then we'll come back and give you the answers. But what I want to just point out really quick, if we look at these answers, 27 and 63 together equals 90. 34 and 56 together equals 90. 45 and 45 together equals 90. So keep that in mind as you're trying to solve these three, that the two of them together, their actual measures, have to equal 90 degrees. So try those, and then we'll come back and show you the answers. Okay, welcome back. So the nice part about this relationship between sine and cosine, since we know that their sum has to be 90 of the two angles, we can take both of our values, 2x minus 1 and 11, and add them together and set equal to 90. And once we do that, it's just simple algebra all the way down. I ended up with x equals 40 for the first one, x equals 15 for the second one, and x equals 44 with the third one. So you've now got some problems to try. There's a lot of problems to practice this. And it only gets easier with practice. So make sure you're doing those practice problems. And if you have any questions, make sure to ask me when you can.